Greetings, fellow mathematicians. This is a really good problem since it stumps a lot of Calculus 2 students. So let's take our time with it so that way you can understand it. Now, we need to first have an idea with the direct comparison test. Should we look for a bigger term or look for a smaller term? To do that, as always, let's go ahead and look at a large N estimation. So let's call the term here a sub n. And we're going to see what happens to that as the value of n becomes very large. Now the numerator is just staying constant as 1, so that's nice. And in the denominator, inside the square root, n squared is going to be much bigger than 1, and very quickly that additional plus 1 will be insignificant compared to n squared. Now be careful with the square root. The denominator behaves like the square root of n squared, and if you simplify that, the square and square root cancel out. N is a positive integer, so this comes out to 1 over n. Now, you should be able to recognize this as the term for the harmonic series, but this is also a p series where the value for p is 1. And since we have that, that is a divergent p series. Now, how this helps us is we now have the suspicion that our infinite series, well, it kind of behaves like a divergent infinite series for large values of n. Since we suspect our infinite series is divergent, we want to look for a smaller infinite series that we know for sure is divergent. And that's where this one gets a little bit tricky. So let's go ahead and start with this. And our work here just tells us that we're going to look for a smaller term. And again, make sure you're comfortable with the conclusions for the direct comparison test. What we're going to be using here is if the smaller infinite series term is divergent, then the bigger infinite series is divergent as well. All right, so let's go ahead and take our term a sub n, which is 1 over the square root of n squared plus 1. And we're going to try to find a term that is smaller. Now remember, with a term, a fraction, you can make it bigger by making the denominator smaller. To go in this direction, with your term, finding a smaller term, we're going to make the denominator bigger. And what we want to do is somehow try to get the n squared and the additional term there to combine together, so that way we can make use of this cancellation like above. And what we're going to notice is for all values of n squared is going to be bigger than 1. So to go from your term to this one, let's make the denominator bigger by replacing the 1 with n squared. All right, make sure you realize what we're doing. We're taking our term and we're looking for or finding a smaller infinite series term by making the denominator bigger, replacing 1 with n squared. Now this helps us. We have like terms here inside the square root. We can go ahead and add those together. And if you apply some properties of square roots, take the square root of each factor, 2 and n squared. And we get it basically as 1 over n, which is what we found above with the large n estimation, but we have an extra factor of 1 over square root of 2. Well, that factor, that doesn't change the convergence or divergence of an infinite series with that term. So we're pretty much done. All we want to recognize is that the infinite series with this term, and I'm just pulling that 1 over square root of 2 factor out front. Since that infinite series is divergent, and again, that is a divergent p series where p is 1. Since the smaller infinite series is divergent, the bigger one is divergent. And that is our given infinite series here. This is divergent. This one's a little bit trickier, primarily for this step right here. And again, how we did that, we took our term, we suspected we wanted to find something smaller because the large n estimation gave us a divergent infinite series. So we take our term, we find something smaller by making the denominator bigger. Very simple trick, but take some practice to really get comfortable with that. Hope you enjoyed the video. As always, like and subscribe.